Everybody. That was really lame. Let's try that again. Good afternoon, everybody. Much better. So welcome to Azure Data Center Architecture. My name is Mark Arsenovich. I'm the Chief Technology Officer of Azure. I've been in Azure since 2010, the middle of 2010, so it's been over 9 years, and it's been an incredible journey. I've been giving this talk for a few years now. How many people have been to a version of this at previous Ignites? Just to raise your hands. It's great to see all the repeat customers. Welcome to the people that haven't been here before. Just to give those of you that haven't been here before an idea of what I'm about to share with you over the next 75 minutes, it's a tour through Azure's architecture, starting with the overall region designs, down to data centers, to servers, and then taking a look at the software infrastructure services, starting with networking, then going to storage, and then finally we'll end up at applications and compute. And those of you that have been here before know that this is chock full of demos. In fact, I'm going to set a record for the number of demos in this one with 9 demos, and some of them are pretty amazing, I think, so you'll hopefully enjoy them and get insights not just into how we're building Azure and some highlights of the ways that we build it, some of the innovations that we're making in the platform, but also I've got some things that we're coming out with over the next 6 months, 12 months to give you an idea of where we're going and filling some of the feature gaps, adding some cool new innovative functionality to the platform to get you excited about where we're going, not just where we are. So with that, let's go ahead and get started. I'll start by talking a little bit about our data centers. And with that, I'll talk just a little bit about our regional strategy and architecture for the way that we build out around the world. And you've probably seen this slide now several times here at Ignite. If you've gone to any of the Ignite sessions, Satya had it in his keynote. We're in 54 regions around the world. We've got many more that are in various states of build out. We're not ready to talk about. You can see that there's 2 that are in the process of lighting up that we've already announced. Those are Azure government regions. Just to give you an idea of where those are, one of them is in Virginia. The other one's in a place that's better known as the Republic of Texas. It's it's its own kind of special little state. And then we've got a bunch that we've lit up recently, including the fact that we were the first to end up in the African continent. We're first to end up in UAE. We've got data centers that are they just lit up in Norway, so Scandinavian data centers. So we're basically becoming a fully global cloud where we're going to have regions everywhere. Now, when we go into a region, we define geography first, which is a boundary where we expect customers to be comfortable having their data replicate anywhere within that boundary. So more and more that's becoming a country, and you see that in the reflection of the way that we've started to build out. When we talk about Norway, that's a geo, and within Norway we've gone in with 2 regions. That's our current strategy, is to go into a geo with 2 regions, and the reason we do that is so that you can do DR. And this is one of those things you don't really think about until something happens, and then you start to think about it, which is what happens if one of the regions goes down. Regions are close enough together, they've got to be within a 2 millisecond latency envelope of any data center to any other data center to meet kind of the local replication requirements that services have. But that means that it's within about 100 kilometers, the data centers of each other, and that puts the boundary small enough that a large-scale regional disaster could actually take out the region. Hurricane, earthquake, for example, and so we've got second regions that can serve as DR sites, so you can fail over from one to the other, that are typically hundreds of miles away. Within a region, we are defining what are called availability zones. In those availability zones, we've got 10 of them operational, there's more coming online, and our strategy going forward is effectively to have at least 1 region with availability zones in every geo. With availability zones, we've got at least 3 distinct data center sites that are physically isolated and also logically isolated. And that means that whether there's a flood, even local flood inside the data center or around the data center, or there's a power problem or a network problem, that it only affects one of the availability zones. And they're close enough together, under a 2 millisecond latency envelope at the worst case, so that you can synchronously replicate data between those availability zones. And so this is the way you provide high availability as opposed to disaster recovery you get with the region pairs. When you take a look at the way that we're connecting these things together, we've been building out over the last 2 decades a dark fiber network, which is one of the largest on the planet. You can see that we've got 130,000 miles of cable connecting our regions together. We've got 160 edge sites to provide close entry points into our dark fiber. When your traffic enters our backbone through one of those edge sites or through one of our data centers or network exchanges and travels to any Azure region from there, it's going over our dedicated dark fiber. And this is a place where we're making huge investments. Those of you that have been to this session before probably saw me talk about Maria, the subsea cable. It's the largest bandwidth subsea cable connecting Europe and US. We did that as a joint project with Telesys and Facebook. It's 160 terabit of network cable connecting those two over 4,000 miles. And so that's the kind of investments we're making so that we can be your enterprise network backbone. When you take a look inside of one of those particular regions, we also have redundancy where we're connecting every single one of our regions at least twice to our global WAN. And that means that if one of those routes gets cut off, there's always another route out of the region. And the way that we're architecting that is using something called regional network gateways. Regional network gateways, or RNGs, are the way that we provide scalable connectivity within a region where we can scale out to many, many data centers in a region. We've got t-shirt sizes that go up to 500 to 80 megawatts of capability of supporting those regions. And you can see that there's multiple routes connecting the data centers to each other. There's redundancy at the RNGs, so there's failover in case one of those RNGs gets impacted. And those are far enough apart too, like AZs, so that local incidents don't impact the routes out to the global WAN or between the AZs in a region. So that's a little look at the network architecture from a physical perspective. Now let's take a look inside of a region and see what these data centers look like. Because I think that looking at pictures and dots on a map, while that is impressive to see all those dots, actually looking at data centers is kind of viscerally telling you just the kind of scale that we're getting to in the public cloud now as enterprises are moving. And I thought I'd highlight that by showing you one of our regions. It's one of our larger regions that we're building out continuously and have been building out over the last decade, and that's in Dublin. Anybody here from Ireland? So a few people. Those people that are from Ireland, you'll see that there's like two cooling towers that look like cooling towers there above that DB4. Those are actually, this being Ireland, those are actually, I believe, towers to hold Guinness in reserve. There's the reservoir there. But these, just to give you a timeline of the build-outs, this DB3 was completed in 2010, DB4 was completed in 2013. I'm going to zoom out, and there's DB3 and DB4. DB5 was completed in 2014. I'm going to zoom out again. And there's where we were just looking at. This is DB6. This was finished in 2015. There's DB7, which was completed in 2017. And then DB8, which was completed in 2018, and then this is where we're building more data centers. So that gives you an idea of the kind of scope and scale that we're getting to with some of these regions. We've got other types of regions too that have completely different architectures just because they're forced to. This is a picture of a data center in Singapore. You can see Singapore, not a lot of land, so we build up instead of out. And this is one of the AZs in the Singapore region, which is AZ enabled. And then I thought I'd just show you some of the pictures as kind of being infrastructure geeks that you probably are, just to see how many people recognize these parts from inside and around a data center. Anybody know what this is? I mean, it looks like a robot or a vacuum cleaner. Yeah, it's a drive shredder. This is one of the drive shredders because we never let media leave our data centers without being completely destroyed. And then this, anybody recognize that, what that is? This is my vacation home on top of the data center in Quincy, Washington. No, it's actually an HVAC system on top of the data center. Now, one of the questions that I always get is, what are you doing about sustainability with their regions? And Microsoft, as you're probably aware, is very committed to the environment and sustainability. And just to give you an idea of some of the projects that we've launched, this solar project that we launched in Virginia, that's the largest corporate solar agreement ever made in the United States. There's 750,000 solar panels on 2,000 acres that are going to deliver up to 500 megawatts at capacity when that project's completely done. We'll be the largest consumer generator of solar power in the state of Virginia when we get to that point. And then the wind program that you see there, that's in the Netherlands. Lots of wind in the Netherlands. We announced that in 2017. We purchased 100% of the power from a 180 megawatt wind farm. It has 100 windmills, and I can guarantee you that we've done validations and none of those windmills cause cancer, so we're all safe there. And then we're also focused on PUE, improving the efficiency of our data centers, and that's been continuously going down as we build out new data center designs. Every data center gets more and more efficient. If you take a look at the average PUE across all our data center footprints, and more than 100 of them over the last 12 months, we have a PUE of 1.189. And that doesn't reflect the state of the art where we've got the data centers that we're building out right now have a PUE themselves of 1.16. So we're always trying to innovate though and make our data centers even better. And some of you might have seen this at a previous session. Project Natick. How many of you have seen this? Raise your hands. So this is our underwater data centers. We made a lot of attention when we first announced the version 1, which is just dropping a rack into 25 feet of water for a month. This is version 2, a little more ambitious. This is dropping 12 racks. It's got 480 servers in it, and we dropped it off the north coast of Scotland. You can see here's a picture of it being dropped into the water. Now this project offers a bunch of interesting experiments. First of all, provides really fast time from signal to actually being live. And that's what we call it when we see demand to having that demand satisfied for our customers. We went from deciding we wanted to do this project to having that container built and then dropped and turned on the ocean floor and running Azure services in 90 days. And by contrast, a land-based data center traditional build-out would take anywhere between 18 and 24 months. So this promises a really effective way to get data center capacity up and running. The other aspect of this is that we vacuum seal those cylinders. So all the air, all the particulate matter, there's no dust floating around, there's no humidity in there, and so that's going to promote server lifetime. Further, you drop them on the ocean floor, they've got constant temperature. We don't have to pay for cooling because that comes from the ocean currents, and we do guarantee that we don't have any significant effect on the ocean temperatures with these things. And that means that our servers are going to last longer. Now, we're already performing experiments where we're doing equivalent land-based deployments. By the way, this is how we're watching with AI for Earth. The Microsoft research people are watching what goes around these data centers just to make sure they don't have any impact. But the PUE of these data centers is 1.07, so even a drastic jump in data center efficiency. This already we're seeing 7x performance improvement in server lifetime and part lifetime compared to the control on land with the exact same servers from the same batch running a land-based data center. So this already, after 16 months since we dropped this in the ocean floor, is showing us that this way of operating data centers can have a significant improvement on the ROI that we've got and the maintenance costs and other factors. Now, we're also embarking on a version 3. This is the first time this has been publicly shown, which is to put these together in these lattice systems that connect them together with power and networking. So you can see that there's 12 of those cylinders that we just saw wired together. This is about 5 megawatts of total capacity. And this is enough for a Azure region, a mini Azure region. And we can build ideas on putting multiple of these together to create expandable Azure regions on the ocean floor. Give you an idea of the size of these things. We've got a setup here in Seattle Stadium, in the Seahawks Stadium. This also happens to be the best pass rush defense for the Seahawks. And the Patriots are so worried they're trying to figure out how to deflate it. Any Patriots fans in here? So that's a look at our data centers. Let's take a look at our servers. And for this, I thought I'd give you a walk down memory lane. You might have seen this before. Our Gen 2 servers, when I started in 2010, this is what we were deploying. And they're AMD Opteron servers. There's 12 cores. There's 32 gigabytes of RAM. There's a 1 gigabit network switch on them. This is the way that we thought the cloud would go, is low-cost commodity servers scaling out. what we started to realize just a few years into Azure, so around 2014, is that enterprises wanted to move big in-memory databases to the cloud. And so we introduced this, and we called it Godzilla. We called it Godzilla. This is the G series of virtual machines because we thought they were monstrous. 512 gigabytes of RAM. They've got 9 terabytes of disk on them, so they're pretty beefy systems. But if you start to take a look, here's our latest generation, the one that we've been deploying over the last couple of years, are Intel Gen 6 servers, and you can see that it already has more RAM than we had in our largest supersize servers just a few years earlier. We're deploying AMD servers now. So you can see that we've got AMD Gen 6. We're starting to deploy our Gen 7 servers. And one of the things you'll see as you look through these is that we've gone from 40 gigabit to 50 gigabit on our HPC SKUs. We've started at 40 gigabit InfiniBand. We went to 100 gigabit, and we're at 200 gigabit InfiniBand. So the speeds and feeds for the cloud infrastructure are continuing to grow and actually accelerating. You're going to see 100 gigabit, 200 gigabit. We're already in line of sight to 400 gigabit Ethernet. And then equivalent kinds of speeds also on InfiniBand. But we've also, in the last few years, introduced even larger supersize VM types. Just to be clear, that we're talking about servers that support our VMs for those in-memory databases. Here's one that we released a few years ago. This we called Beast. And we called it Beast because it's got a lot of RAM on it. It's got actually 4 terabytes of RAM on it. And we thought, wow, that's really big. But then our enterprise customer said, we've got even bigger in-memory workloads we want to move. And so we just recently released this, Beast V2, or Son of a Beast, I like to call it. And this is 12 terabytes of RAM, 448 cores. And so things are getting bigger. But Azure is more than just about data center hardware. We're also on the edge. And we have the opposite extreme, which is kind of nice, which is here's Azure Sphere. And it's not quite in scale there. We had to actually show a little black dot there. But you really wouldn't be able to see it because this is like 0.0000 something of a Beast V2 in size. We're also pushing the envelope with our hardware partners like Micron to deliver innovations that come to the cloud first and that even have Azure-specific enhancements on them. So this is the Micron Scudi-O. It's codenamed Scudi, named after a star, and the O stands for I/O. This is a 3D crosspoint powered device. So it's going to provide way more performance than a standard NAND type SSD device. It's going to provide lower latency. It's going to provide more bandwidth. This is the fastest disk on the planet. And if you don't believe me, I want to show you a little demo here of it in action. Uh-oh. I forgot my pin. It's a demo. What? Oh, it's on the sheet. Okay, good. Nobody look at the sheet. All right, so here's the Scudi-O demo. I've got 2 VMs here, 2 Azure VMs. One of them has a standard NAND type SSD attached to it. The other one has a Scudi-O SSD attached to it. And I've got a iometer, which is a disk benchmarking tool. I've got it configured to show us the throughput in megabytes per second. I'm going to start it on both of them, and let's see how they compare. So about 2 megabytes per second, not bad. 9 megabytes per second on the Scudi device. That's it? No reaction? That's all right. So then maybe that didn't wow you enough. Let's take a look at a TPCH run. And this is one of the TPCH tests. So we're going to run this test and see how long this takes on the standard NAND device. And you can see that the kind of network, it's kind of disk latency we're seeing on the queries here. It's about 20 milliseconds, 20 to 25 milliseconds. And we just finished the test, and that took 18 seconds. So let's go take a look at the Scooty device now. Same test, same TPCH test. Run the test. Now you got to watch really fast and close because it's done. The transfer times are about 2 milliseconds, so about 1/10 the latency on the Scooty device. So pretty impressive, and those are coming to an Azure data center near you. Now some other of the cool innovations we're working on with another hardware partner, this one being AMD, is partitioned GPUs. Because one of the challenges we've had is when we want to give customers GPUs, we've had to provision a GPU per VM. Because up till now, you haven't been able to reliably, with good quality of service, take a GPU and split it up into sub-GPUs. And that's what we're able to do now with this AMD Radeon Instinct M125 GPU. This GPU has 16 gig of RAM on it, but we can carve it up into fractions, down to 8 gigabytes, 4 gigabytes, even 2 gigabytes. And so you can see if you've got a full graphics workload or a full Bitcoin mining workload, you can take the whole 16 gig. Okay, so nobody is mining Bitcoin in here. Then you can see if you've got lighter workloads, we can give that to you too in smaller VM sizes. And I want to show you that really quickly. By showing you first this architecture, you can see here that we've had to write special drivers for the hypervisor and guest components to work in the hypervisor that are enlightened to the fact that these things are partitioned in this way. But once we have those in place, we can show you a GPU running in a partitioned manner. So let's take a quick look at that. And I've got a VM here. It's my partition VM. Here, you can see this is hypervisor on the host of one of the Azure servers. It's got 4 VMs on it. And those 4 VMs, we've got 3 of them showing. One of them has 16 gigabytes of GPU attached to it. The other one has 8. The other one has 4. You can see that there's a bunch of GPU activity in the middle one. These are all sharing the same physical GPU. This one's actually running a stress test, pegging its fraction of the GPU. But in the other VMs, you see 0 activity at all. These have that full dedicated amount of their partitions of the GPU available for their use, as if it was an exclusive physical device just for them. And this is what's going to make it much more economical for us to provide GPU capabilities like this way in the public cloud. For example, Windows Virtual Desktop will be taking advantage of these. And that's, again, an innovation with a hardware partner, in this case, AMD. We're also pursuing other advances in the data center infrastructure, kind of experimental, where this is where we're doing things ourselves rather than waiting on the ecosystem to do it. One of them is liquid cooling. The reason that we're pursuing liquid cooling is if you look at the trends in CPUs and GPUs, the amount of energy required to power some of these high-performance graphics parts. For example, you can see this NVIDIA DGX2, which consumes by itself 10 kilowatts of power. Now, today in our racks, we're power provision for about 14 kilowatts. And you can see as the CPUs get more powerful, still we've got a case limit on thermals in the data center as well. So if we want to get more power packed more tightly, we can't rely on air cooling. And that's what we've been doing up so far. We've got some of the world-class air-cooled system with our Olympus design, which we've contributed to the Open Compute project. But we're investigating multiple types of liquid cooling, including microchannel cold plate, which is where we've got coolant running over through tubes that are touching the servers and GPUs. This is kind of what you would use at home when you're using liquid cooling. But we're also pursuing immersive cooling systems. Maybe I need to be close. Here's one phase immersion. This is where we're dropping the motherboard or the main board into the liquid coolant itself. You can see there it gurgling from the temperature. And then, even more exotic, 2-phase immersion. We drop the whole thing in. And you can see this is a liquid with a very low boiling temperature, which helps as it evaporates, cool and release that energy off of the servers. And this looks extremely promising, these different technologies, different cost, performance, complexity trade-offs, and management trade-offs inside the data center. But we're pursuing all three of these different projects in parallel, and we'll be probably rolling out at least one of them into our data centers in the near future to provide more efficient packing of servers. Now let's take a look at our networks from a logical perspective. And networking consists of a whole lot of different services. If you take a look, we've already kind of covered the physical aspects there from our regional and WAN architectures. We've got edge sites and express route sites that connect into enterprise backbones as well directly, but then it's a whole bunch of software-based services on top of it. So we have physical networking and we've got software-based networking, or SDN. They go together. And part of this is being able to design virtual network topologies that connect your enterprise networks into Azure seamlessly, be able to route traffic wherever and make it as easy as possible. Instead of having to be network engineers and manage specific routes, you start to manage things logically by the application with network security group rules and even better, application security group rules. Now, as customers have started to move their most sensitive workloads to the cloud, one of their requirements is I want my stuff in Azure protected from the public network as if it was in my own data center on my own sealed off enterprise network. And so we've recently introduced a feature called Private Link. How many of you have heard of Private Link? So a few of you, and those of you that probably have been the ones that have been looking and asking for this as you've moved very sensitive workloads. What Private Links allows you to do is take a PaaS service. And initially we have Cosmos DB and SQL and storage coming, and Key Vault will be coming, and eventually all Azure services will have support for this. So we're starting to roll this out across all our services. But you'll be able to take one of those services and say, I want that service endpoint plugged into my subnet, my virtual network subnet, so that I can access it using a local IP address from my Azure VMs or other Azure resources. And when you do that, this service is not available outside from any other place, from any other virtual network or from the public internet. So it's like hence the name Private Link. It's a private link into the Azure PaaS service. Not only can you do this with Azure services, you can take your own services and do this as well. So you can take your own SAP HANA, for example, and plug it in to a virtual network subnet that another virtual machine accesses as if it was in its local 10 space. And that way, the SAP virtual machine doesn't have to be on the internet. The benefit of this, besides that, is that it simplifies your network rules. Because one of the things that a lot of security-sensitive customers want to do is just say, I want this virtual machine not to be able to talk to anything outside. No internet access at all. So let's take a look at that in action. So here I've got the Private Link setup wizard. So you can see the Private Link center. And there's a few different services, like I mentioned, ways to use this. One of them is to create a resource of your type. And you can see storage, SQL, SQL Data Warehouse, Cosmos DB. I'm going to create a SQL database and just show you where you get to the place where you say, I want this thing to be completely private, which is here on the networking page. There's an add a private network. And when you click that open, and you'll be able to create the private network. And one of the cool parts of the private network is you're able to integrate it with a private DNS server. What that means is the PaaS service DNS name shows up in the DNS for the virtual machine you connect it to. So you can access the service using its DNS name like you always were able to, but the traffic gets routed through the private IP address that's part of the subnet you wire this into. And if you go take a look here at the final setup for this, you can see that this SQL database has an FQDN, as normal, Ignite 2K, database.windows.net, but it shows up with a private IP address, and that private IP address is from the subnet in the virtual network that you said that you wanted this thing projected into. Now, if I go take a look at this virtual machine that I'm going to use as the client virtual machine to connect to it, and I go to its network settings, and I go to outbound port rules, the first rule here, notice it, deny outbound internet, any port, any protocol, any source, deny. That means that this virtual machine will not be able to access anything outside. And we can show that. I'm connected into that virtual machine. I'm going to ping Microsoft, and it's going to fail because this thing is blocked by network security group rules from talking outside. However, because it's on private link, you can see that I've got a SQL Server connection here, and you can see Ignite 2K, that DNS name that I specified before. And when I connect, it's able to connect right into that. On the other hand, back in the outside world, I'm not able to see that or resolve that address to anything that I can connect to. And so this is an example of private link sequestering off that SQL database instance so that only that virtual machine can access it, and I've got a virtual machine networking rules so that it can't access anything in the outside world. So that's kind of your virtual private data center in the public cloud enabled with this capability. Now, if you think that was cool, which I hope you did, there's something even better. This demo is even cooler. It might be my favorite demo of the session. This is called Azure Bastion. How many people recall me? I think I talked about Azure Bastion last year as a preview. So I'm previewing some more advanced capabilities of Azure Bastion. How many people have used it? Anybody used it? So a few of you. What this does is let you connect into a virtual machine using RDP or SSH, even if that virtual machine has no inbound network connectivity at all, has no IP address. And this basically lets you access anything completely securely through Azure's infrastructure without having to expose that virtual machine to the outside world, but still be able to do diagnostics on it if you want to. But I've got some cool new features that I'm going to demonstrate to you in this demo I've got right here of Azure Bastion in action with these new capabilities. So if I go and I take a look at this virtual machine right here, my WinVM, one of the things to note, the big thing to note, is that it has no public IP address. So this thing is just not accessible at all from the outside, only inside of its virtual network. However, when I say connect, and I want to go do some RDP actions on it, I'm able to connect an RDP into it using Azure's infrastructure, where Bastion is connected. Now watch this. Notice what I'm doing. Okay, that didn't mean anything. And I don't know PowerShell, so it doesn't matter. But this is the cool part of this. This is a storage account. I'm going to press refresh here. And there's a blob in that container. I'm going to download that blob and then open it. So one of the things you want, especially when it's a security-sensitive VM, is what did the person do when they RDP'd into it or SSH'd? And here you go. All right, if that's not cool enough, wouldn't it be cool if you could use Bastion to connect to any resource anywhere, even if it was outside of Azure? Yes? Okay. I've got a Raspberry Pi device sitting on a network engineer's desk back in Microsoft. So I hope he doesn't kick it off while we're in the middle of the demo. And I'm going to web connect to it using Bastion. This device, this is a Raspberry Pi I'm connecting to over in Redmond through Bastion. The thing is not on the internet. In fact, just to prove to you it is a Raspberry Pi, there, Raspberry Pi. And to prove to you that it's not on the internet, it's on the Microsoft guest Wi-Fi network back on campus. And not only that, it's got a private IP address there. So you can see 10.69. This is an IP address on Microsoft's network, but it's connected through Express Route into a virtual network in Azure, so I'm able to bastion into it. And so with that, I'm able to securely access resources even if they're outside. So you can now use Bastion from Azure to connect into your virtual machines back on your corporate network using this capability. So let's take a look at storage now. So we've taken a look at data centers, servers, networking. Let's take a look at what we've got in storage. And the basic storage architecture, and what I'm talking about here is blobs and files and disks. And this is simplified. This is looking at the mainstream storage service, which includes blobs, premium disks, as well as queues and tables are all built on top of this architecture you see right here, where there's multiple layers there. And this layered architecture from front ends, well, so API servers and front ends, to partition servers, to the stream layer or extent layer that manages the actual chunks of data on physical disks, has been there from the start of Azure. But over time, we've added more and more capabilities. There's more and more, you can see, APIs on top. From HDFS, for example, has been added not too long ago with Azure Data Lake Gen 2. We're working on NFS, so we're working on NFS v3 and v4 are in progress. So, and you're likely to see more APIs, file-based APIs show up on top of this architecture. But one of these things that we've been re-architecting over the last couple years is allowing these standard clusters to connect together, and that provides a bunch of benefits. One of them is that we've got things like high throughput block blobs, where we've got front ends that are caching data from multiple blobs, so that provide faster access to your blobs, and by connecting these things together, we get higher throughput overall because of all the network pipes coming out of these combined sets of stamps. Plus, you can see down at the stream server layer, the extent layer, that they're able to borrow disks from each other and store their data on them. And so that means now we're going to support basically limitless storage account sizes and effectively limitless blob sizes as well. The goal of this architecture is to get to full AZ and then regional size capacity. So you'll be able to take, not that anybody will, but allocate an account with a blob that consumes every single byte of storage service inside an entire Azure region. That's our goal with this architecture, then we're on our way to creating. And then you can also, of course, geo-replicate. And Azure Storage has had geo-replication capabilities that you see over the last year or so, new capabilities coming into, like the ability to do a controlled failover yourself and to fail back. And there was read-only GRS, where you can read from the secondary at the same time. But one of the things that we've been asked from customers is, hey, we want to replicate to arbitrary regions. And so you'll be able to take GRS and pick your region that you want replication to. We're also working on something finer grained, and this is object level geo-replication, where you're able to take and set a rule or filter on which containers you want and what blobs in them you want replicated, and be able to specify arbitrary destination storage accounts where you want the replication to happen to. So here I'd set a policy on the source storage account. That policy would apply to particular containers and blobs inside that container. The replication service is watching for changes, and when I say I want to replicate to a destination, the replication service starts replicating and keeping track of the progress, and this would be a eventual consistency type replication, but you'll be able to query where it is in the replication process. And eventually the goal is to have you be able to replicate one storage account or storage objects to everywhere in the world, just kind of the Cosmos DB model of you want replication anywhere, replicate wherever you want. So that's something that's coming, not quite here yet. The other thing that we've got coming, not quite here yet, in the spirit of showing you where we're going with Azure, is being able to put more intelligence into the service. And you see this trend across storage services in general, with things like Synapse, is putting more intelligence directly into the service so you don't have to do things outside that are more efficient inside the service itself. One of them is being able to look up objects by some kind of tag. So with Azure Blob Index, you'll be able to assign a special kind of tag, key values, to your Azure blobs. And once those tags are assigned, there's an indexing service that's going to be indexing those tags. It's maintaining a master index of all those tags for you so that when you do a query and say, hey, return me all of the blobs that have matches, kind of a SQL syntax of this is less than that, or this equals that, or this and that, it's going to go and query and return the names of those blobs to you that have that match. And so this is a way for you to efficiently go looking for information and zooming in on it. But now once you've found it, how do you look inside for data that you want out of that? Well, we've got another service that we're coming out with called Azure Blob Quick Query. With this one, you'll be able to have JSON or CSV formatted data in the blobs and be able to execute SQL queries on it once you've said you want those things indexed. And so we've got working with Microsoft Research on a very efficient CSV scanning implementation. It's the most efficient that in existence so far for being able to query CSV. And if you think about it, those fragments of file that we spread across those disks, they have arbitrary cutoff points between them when it comes to CSV or JSON. So one of the hard problems here is how do you do a CSV query, like a regular expression, across these kinds of fragments efficiently. And so that's what we've been able to do. And so with that, you'll be able to send the query down. We'll be able to figure out which disks the query applies to, send the queries down to those disks, do the queries, aggregate the results back up, and then return them back up to you. And so that is that in action. So let me go show you a demo of Blob Quick Query in action. So first I've got a bunch of blobs, and actually this Storage Explorer is only showing that I've got 1,000 cached items. There's actually 38,000 blobs in this storage account that have this name format to them. Ignite 2010 something.json. They each consist of JSON data between 1 and 2 gigabytes of it. And so we're talking about terabytes and terabytes of data. And one of my goals here, this data happens to be library information from libraries all over the country, including Seattle. And so what I want to do is just find out how many books of mine are in the Seattle Public Library system. So we've tagged these by library, and what I'm going to do is go into Quick Query and do a lookup. So this is calling the Blob Quick Query APIs to look up on the tags. So you can see out of those 38,000 blobs, I got an answer back very quick. These are the blobs that match a tag of Seattle. Not all of those are public library. So there's the Public Library of Seattle JSON file for what all of the books they've got in their catalog. Now I'm going to use the local quick query there to query that particular blob and select title from blob storage where author equals me. And there better be a lot of them. Now, remember, we're querying over 2 gigabytes of JSON data. The traditional way you have to do this, is either set up some kind of analytics cluster to go query it, or to suck it out and then do a query yourself. And imagine, especially on the Wi-Fi network here, having to suck out 2 gigabytes of data from the cloud and then do a query. Are you having better Wi-Fi experience than me? Okay. Okay, there we go. It just finished. So that's a look at the quick query and the kind of trend that we see coming with Azure, with storage services in general in the public cloud. Now, the next thing that we've got coming is one of the things that we've been asked for repeatedly is, hey, I want to take my Windows Server failover clustering into the cloud, or I've got some other clustering solution that requires shared disk. So with the primitives that you're familiar with of doing a reservation on a disk and then being able to release that reservation and fail it over so that only one of those disks is an active writer from a virtual machine at the same time, the same kind of architectures you've got on-prem. How many people have these kinds of architectures with SCSI reservations on disk and failover clusters? So quite a few of you. Not available in the public cloud on virtualized infrastructure until this comes out. So we're working on this, and this is going to be out soon Azure Shared Disk for both premium SSD as well as Ultra SSD disks, where you'll be able to set them up in this configuration and say, I want these set up in this so I can fail over from one. And the same primitives are supported, so any off-the-shelf, like Windows Server failover clustering, you deploy it in these things, and you'll be able to get your failover cluster running inside of Azure without a modification. The storage team is looking for customers that want to try this out, have workloads you plan on moving that are like this. And so there's a URL right there. So go click on that if you're interested in engaging with them and seeing if you can get into the private preview. So finally, let's talk a little bit about compute. And compute's a big topic because there's lots of layers and types of compute. And I'll start at the very highest, broadest view of what we see as compute, which is the control plane to Azure, Azure Resource Manager. When you take a look at Azure Resource Manager, it is the front door effectively for all of Azure services control planes. And what Azure Resource Manager is responsible for doing is keeping track of a whole bunch of data about Azure itself and all of the services, including all of the resources, the subscriptions, the tags, metadata, the resource types, and the resource instances that have been provisioned. It's managing literally hundreds of millions of resources right now that all of the accesses to go through the control plane. And because they all go through Azure Resources Manager's control plane, you get standard APIs and you get standard controls on top of it. One of the differentiators of Azure's control plane is that it's global. So you'll note that when you go to Azure's portal or the CLI and you want to query your resources, you don't have to point at a particular region and say, show me the resources in that region, now show me the resources in this other region. You just say, show me my resources, and you see them all from everywhere. And that's because Azure Resource Manager is doing global replication of all this subscription information, metadata, and resource instantiation information across all of our global regions. Today, it's been using custom replication service, but it's moving on to Cosmos DB for this right now, so that it's going to be just riding on the back of Cosmos DB's global replication capabilities. But that's one of the big conveniences you get out of Azure Resource Manager. But like I mentioned, one of the other cool things about Azure Resource Manager is that anything that plugs into it, and you see all the Azure resources that plug into it, anything that plugs into it automatically gets role-based access control, gets plugged into Azure Monitor, gets policy, and higher level services that plug into particular resource types or that plug into those, like looking at Azure Monitor for potential signs of breach, like Azure Security Center would, automatically get those capabilities. And that's what Azure Arc is all about, is taking other resources that are not in Azure and plugging them in to Azure Resource Manager. One of the examples of Azure Arc is the Azure Arc for servers, where you can put an agent in your servers, and once it's in there, now you're starting to get policy and RBAC controls into what goes on into those servers, as well as managed service identity as well. So now those servers can talk to Azure resources and have their credentials managed automatically for them. And that's through the power of them plugging in through Azure resource providers into Azure. We're making it possible right now for third parties to write their own custom resource providers, or custom RPs we call them, and also creating a platform so that you can create a custom RP really simply on top of Azure Functions. So with very little effort, you'll be able to write an RP, a custom resource that will show up in Azure. Once it's there, you can access it through the CLI, through PowerShell, if you want to use PowerShell, through the portal, and you'll be able to use it in Azure Resource Manager templates as well. Now, is that a PowerShell clap? Now also, we're also focused on enhancing our platform capabilities as well in terms of performance and reliability. One of the ways we're enhancing performance is through a service that we've been rolling out called pre-provisioned virtual machines. So by its definition, the stand-up of a virtual machine with an operating system on it and disks attached to it and virtual networks and network adapters is a fairly complicated operation that consists of interactions across dozens of Azure services, all the way down to the server. If you take a look at ways to speed that up, we do things like prefetching the images, but one of the big steps we've been making is to pre-provision servers virtual machines. So we pre-allocate the VMs, and this has been a challenge with Windows, is how do you do this in an orchestrated, graceful way so that virtual machines are now running with a system provisioned image. They're up and running, and when a customer comes along and says, I want a virtual machine of this type with this OS in it, that we connect it to that virtual machine. It's there sitting ready for a customization ISO to attach to it once it does with what you want the host name to be, with how you want it to be configured inside. It then applies that information and does a quick reboot, and now can be provisioned in seconds, much faster than if you had to go through the double reboot and actually wait for the whole rest of the control plane stack and data plane to get that virtual machine ready. So let me show you an example of pre-provision in action. Now, pre-provisioning supports everything from Windows 7 and Server 2008 R2 on up. It relies on machine learning to look at patterns that you've got for the way you deploy virtual machines. What sizes you use, what images you're using, what regions you're going into, and learns from that. So the more you do, the better it gets at predicting and having a virtual machine ready for you. And so I've got an example of the comparison between the non-pre-provisioned path, which is the one that you've probably been using, and the pre-provisioned path, which is the one that you'll be able to start taking advantage of. So here's what I'm going to do is actually here. I've got a deployment script which is going to deploy a Windows Server VM. And while that's deploying that Windows Server VM, including deploying the resource group into it, you probably might have seen this. This is an existing virtual machine I deployed a little while ago and ensured that it didn't get pre-provisioned treatment. And you can see this is the kind of typical experience you'd get today when you deploy a Windows Server virtual machine in Azure. About 2.5 minutes. So not horrible, not terribly great either. We wish we could do better, and let's go take a look at how we're doing with pre-provisioned virtual machines. And so that's the fastest Windows virtual machine provisioning in the public cloud today. And it's just going to get better. So it's not just all about virtual machines, of course. It's about containers these days as well. And so that's another area where we continue to invest heavily, is making the world-class container infrastructure. If you came last year, you might have heard me talk about Swift, which is software-defined networking for containers. And we've been rolling out capabilities for Swift and continue to roll them out. But we're also, in Azure, standardizing on a common containers as a service built on top of Service Fabric. Service Fabric is the microservice container orchestrator that we've been, or container and process orchestrator we've been using in Azure since Azure launched back in 2010. And dozens and dozens of Azure and Microsoft services are built on top of it. It has scale capabilities in it that we can't find in any other container orchestrator. And so we continue to invest in it, supporting our infrastructure from everything from Power BI to Intune to Event Hubs and Service Bus, all of these services and the Azure infrastructure itself built on top of it. So Atlas Control Plane is leveraging Service Fabric to manage the deployment of Hyper-V containers, which are strongly isolated containers, the same kind of isolation that you get out of a virtual machine, onto shared clusters in a hostile multi-tenant way. And using the Swift capabilities, we can give each one of those containers membership in different virtual networks with different ingress controllers and all of the other dedicated capabilities that are typically hard to get on top of a shared infrastructure, especially when you've got these things strongly isolated, where you can put two different customers and containers next to each other. You can see that we've started to migrate our existing services on top of it. And Azure Functions for Linux. Anybody use Azure Functions for Linux? Which GA'd? Python. So that was the first service that took a bet on Atlas shared infrastructure on top of Service Fabric containers and Hyper-V containers. So when you go launch an Azure function for Linux, you're taking advantage of Python. Python, of course, and as well as Atlas. Also, Virtual Kubelet is moving on top of it. Virtual nodes for Azure Kubernetes service moving on top of it. And same thing with Azure Container Instances. In fact, Atlas is agnostic to what API surface you use to launch the containers onto it. So you bring your own model, that model calls into Atlas to deploy those containers with the requirements it's got, and Atlas takes care of the rest. So let me show you a demo of that. And this is a demo of an evolving platform, but I want to give you an insight into where we're going with the platform itself when it comes to first-class support for containers. So here I've got a little demo app, and it's going to be showing us functions, Azure Container Instances, and Kubernetes virtual nodes, where each one of them, you can see I've already got a couple launched just to keep them warm, firing firework kind of things here in Florida. And I've got a Service Fabric Explorer. This is looking at the Azure infrastructure, using the same Service Fabric Explorer tool that you'd use if you develop a Service Fabric application. You're able to look at the applications and replicas that you've got in that. And you can see this is a test cluster where I'm just targeting deployments of these different APIs at it. Note that there's 53 applications deployed on it right now. Then this is the Azure Functions app service that I'm going to be using to execute this. That's listening on a queue, and for items on the queue, it's going to be launching more and more Azure Functions to process them. Here's my Azure Container Instances dashboard. This is where I'm going to be launching Azure Container Instances. You can see there's none of them running. And then here's AKS, the virtual node pool that I've got connected. So when I launch virtual nodes, virtual kubelets, virtual instances, I'm going to be launching them onto this. And these are all mapped directly to that Service Fabric Atlas cluster that I just showed you. Now, when I go into Visual Studio Code, I've just launched a script. That script is doing this. It's starting the queue trigger demo. It's launching a resource group for Azure Container Instances we'll take a look at, and then it's also applying a Kubernetes manifest to create virtual nodes. Here's the queue trigger function. Here's my Azure Container Instances template. You can see that, no, not now. You can see that this thing is a standard Azure Resource Manager template I've deployed to create Azure Container Instances. And then here's the Kubernetes manifest that applied to that Kubernetes AKS cluster to get virtual nodes deployed on it. Now, if we take a look back at the Edge browser, oops, I think let's see how we're doing. And so we're starting to scale up on each of these. We've got 51 functions, Azure Container Instances, virtual nodes, and these will continue to rise as more and more of these get deployed. If we go back and take a look now at, for example, Azure Kubernetes Instances, I'm sorry, ACI, Azure Container Instances, you can see here all the containers that we've launched into Atlas, and then you can see now we're up to 128 applications, and that is because underneath the hood, that's what we're using. And so this, I wanted to give you an idea of how we're building this world-class container infrastructure capability, and yet building on top of the same kinds of technologies we make available to you. So we're also looking at how we can, just like in the case of virtual machines and speeding those up, we're looking at ways we can improve the deployment to containers as well. And one of the things we just launched in preview, and there's a blog post on this, if you go search for it, Steve Lasker, the head of Azure Container Registry Development, published a blog post on this project called Project Teleport. The recognition here is that when you deploy a Docker container, Docker containers consist of layers. Those layers are identified by hashes, and then what you go do is look up and see if you've got those things already cached, and if you don't, you just go pull them. And there's compressed images that you pull down, and you expand them locally onto your local media that you're targeting where their containers are stored. Now that process can be very time consuming. You're downloading over the network, you're expanding them, you've got to wait for them to be fully expanded before, and all the layers stood up before you can start to launch the container. So what the Teleport project does is when you see a request, and this is called the Orca client, which is part of Azure Container Registry, when it sees a pull for images, it looks to see, gets those hashes, it looks to see if it's got them in a the compressed layers for them, and it sees if those compressed layers have pre-expanded versions in an Azure file share, and if so, it maps those Azure file shares directly into the target virtual machines, and those images are basically instantaneously there, pre-expanded. No downloading over the internet, at least not synchronously downloading, because once they're there effectively, you start to execute your container and things get pulled in from the backend file server on demand. And so if parts of those container images aren't even referenced, they're never even read over the network. And at that point, you're up and running. And just to give you an idea of where we are with this right now is being previewed inside of Azure Container Registry. If you use Azure Container Registry tasks, you're leveraging Azure Teleport. And we're going to be rolling this out to other services. But to just show you how awesome this is and what a benefit you get out of this, here's a comparison. If you had your own dedicated virtual machine and you're doing container launches on them of various sizes of images, you can see from 2 kilobyte images, 1.8 seconds, all the way to 5 gigabyte images. And we do see customers with massive images because they've got huge applications with sometimes data sets inside of those layers. So we do see images now up into the multiple gigabytes in size. And you can see that on a dedicated virtual machine, you're talking about minutes to download and get that container running. Azure Container Instances, we've got optimizations in there so you can see, but you get about the same kind of experience. And then Project Teleport, 5 gigabyte image, launching that, if it's been pre-expanded into Teleport, you're now up and running. Your container launches in 7.6 seconds as opposed to minutes. So and the reason why this works inside of Azure, it's harder to do this outside of the enterprise because we've got reliable networks with high performance networking and connectivity to file shares that are operating at scale, allows us to take advantage of these kinds of pre-provision type operations where we're dynamically stitching things together in this way. So this is an example of kind of innovations we get from controlling the stack from the top to the bottom in Azure. Now, one of the efforts that we've been pioneering in Azure is something called Azure Confidential Computing, or ACC. How many people have heard of this? So some of you have, most of you haven't. Let me ask you this question. How many of you wish that when you put data in the cloud that nobody except for you could have access to it? Okay, just wanted everybody to raise their hands, hopefully. That's really the idea for enterprise, and really we want you to be able to achieve that too. So services like encryption at rest and encryption over the network, those are all capabilities that make it so your data is kept private. Kept private from other customers, kept private from us and our operators, and kept private from anybody that happens to break in to the infrastructure. Now, we can go a step further and with some of the latest advancements in software and hardware technology to provide stronger and stronger isolation for data, not just while it's laying around or on the wire, but while you're processing it. We call this protection of data while it's in use. Oh, and I need to be showing you a slide thing. So this is the Azure Confidential Computing Platform. Now, you see there that there's something called a trusted enclave, or a TEE, Trusted Execution Environment. What this is effectively a black box. It's either created by software or created by hardware, where nothing outside that black box can see what's going on inside of it or tamper with what's going on inside of that. You might have heard of Virtual Secure Mode in Windows Server 2016, and Shielded Virtual Machines, which came out in Windows Server 2016. Those are examples of software-based trusted execution environments. But there's hardware environments as well. So ARM has Trust Zone, Intel has SGX, and with SGX, for instance, this is an enclave capability built into later Intel processors where you can say, create me an enclave of encrypted memory, and once that you've created it, it's inaccessible from anything outside, including the host operating system. It's also inaccessible from anybody with physical access to the server. So because it's encrypted and none of the data that's being processed on the CPU ever leaves the CPU complex in plain text form, even to the memory. The memory is encrypted, so nobody that's even snooping physically has access to it. With Azure Confidential Computing, we've provided software support and hardware support for this, both with software support in the form of Open Enclave, which is a SDK, part of an SDK where you can create code that runs inside one of these things and talks to the outside with standard interfaces. And we've created support for it in hardware form in Azure with the first SGX-enabled virtual machine sizes in the public cloud. So literally, you can now deploy data to put data in Azure that's encrypted and then do computation on that data such that we have no technical ability to get access to it or anybody else that's in the environment. And this is the path that we're trying to push the whole industry towards, down this path. And we've been working with lots of customers to validate scenarios that take advantage of these capabilities, in some cases to do things that haven't not really been possible before from a technical perspective, like multiple parties sharing data with each other, where they can be assured that neither party is going to have access to the other party's data. And certainly that the cloud infrastructure provider, the hoster like us, has access to it either. One of our great partners in this is Royal Bank of Canada, which has set up a confidential inference project with us. In this project, they've got retailers, they've got a bunch of historical buying data on customers, and the retailers might come and say, hey, for this set of customers in these products, how likely are they to buy it? And there's a lot of sensitivity on sharing that information on both sides. So what RBC is setting up is this confidential inference service, which has a model that they create off their data. The retailer can provide their data and get an evaluation. And now know that neither Azure nor RBC got access to the retailer's information, and RBC can be confident that the retailer didn't get access to the model. Let's go take a look at that in action, and here's the basic architecture for it. It's essentially what I just described. You can see that there's the customer, there's RBC. The customer is going to create a connection to the encrypted enclave. Once it establishes verification through an attestation service that this is an enclave running on Intel SGX hardware, that it's running in an Azure data center, that it's running the inference model that they trust, they release confidentially their query to it and then get back encrypted results, and nobody else around that has any access or insight into what they're doing. So let's go take a look at that in action. So here I've got the enclave code. So this is the code that's going to be setting up that enclave. You can see here, creating enclave. This is actually RBC's own code. They allowed us to show this to you. This is the API server that is going to be connecting to the enclave and establishing a trusted, verified connection to it to make sure that, hey, like I said, this is an Intel SGX enclave I'm talking to, and it is running the inference code that I trust. And then here's the code from inside the enclave, which is going to be getting an inference request. So this is the encrypted data coming from the outside for that request. It's going to be processing it and returning the data back encrypted to the key that the customer, the retailer, has provided and said, I want you to talk to me using this this key, which only I have access to, that I've gotten out of an HSM in Azure Key Vault. Now let's go take a look at that in action. So what I'm doing is launching an instance of that inference. You can see here's the data that the retailer's got. They've got a bunch of customers and they've got a bunch of products that they're wondering if those customers would be interested in purchasing. And a bunch of, you can see, attributes or features and the credit risk. So then they establish this connection with the enclave. It's a trusted encrypted connection with their own encrypted key. They've got a quote back from the attestation service that verifies that they can trust it. They send their inference request in with that data payload encrypted, and then they get back the result using RBC's model that tells them how likely those customers are to purchase. And all of that done with ultimate confidentiality for both the retailers and RBC's data and model. So that is an example of the real world application of ACC that we're starting to see now that we've got these basic building blocks in place, but over the next 12 months, you're going to see a ton of innovation happen in the world of ACC. Okay, final demo. I might have been wrong when I said that the last one, that Bastion demo was my favorite, because this could be my favorite demo. Maybe it might be yours. Now, how many of you got stickers that I handed out? And I asked you, what is on those stickers? For those of you that, I'll see an image of the sticker on the next slide, but what's on those stickers is a picture of this. This is what's called a water bear, or a tardigrade is its official name. These creatures are about 2 millimeters in size, so they're very small. Now, why are we talking about tardigrades? And you might have heard us talking about tardigrades around Azure. The interesting aspect of this creature is that it's incredibly resilient. In fact, this is the most resilient creature known. It survives at multiple hundreds of degrees Fahrenheit for a few minutes. It survives in deep space. It survives in vacuum. It can hibernate for tens of decades with no food or water. Then it just can get rehydrated. You might have seen, actually, by the way, that the Chinese actually dumped a bunch of them on the moon recently. So go check that out. But so they wanted to go test out there, and they're probably fine. So they can actually also survive very low temperatures, down to 272 degrees Celsius as well. They've been found at the top of the Himalayas. They've been found in the Marianas Trench. They've been found in volcanoes. So these things are they're what we want Azure to be for you. And hence the tardigrade project and the tardigrade name. Now, what do we mean when we're talking about it specifically? The reason that we came up with tardigrade is, and that's now an umbrella term for us, making Azure really reliable, like tardigrades. But we started with this project more narrowly focused, which is how can we make it so that virtual machines can tolerate server problems? So if you take a look at a failure of an Azure server, and this could be a software-based issue or a transient hardware-based issue where we get a signal and it doesn't completely bring down the server, but we know the server needs to reset to get into a good state. We don't want to do what's been happening, which is when the server has a problem, when the server has a problem, the virtual machines just die. The server reboots, the virtual machines restart. Now imagine if that's your 12 terabyte SAP HANA server. You're going to be waiting around a little while for that server, that virtual machine to come back up, and the server's going to take a while to reboot too with 12 terabytes of RAM on it. What's going to happen now with tardigrade is when the server has a problem, instead of, this animation clicker is unreliable. It should be tardigraded. So the server has a problem. We intercept that. We freeze the virtual machines in memory. The server comes back, and then we resume the virtual machine. So I'm going to show you that in action. Oops. So I'm going to be connecting through a KVM into Azure here. And I think this one disconnected, so I'm going to have to reconnect. Yeah, let me reconnect. So this is an Azure server, and it's got a virtual machine on it. That virtual machine, you're going to see both the host view, and here's the virtual machine view. And this host is running a program. Anybody recognize this program, by the way? Well, first note that this virtual machine just got a script in it. that is just counting over and over. And that's going to give us an idea of how this thing, what kind of impact this thing takes and kind of continuity on this virtual machine. But this program right here, it's called Not My Fault. And it's by me. It's a sysinternals demo tool that I wrote for Windows Internals book so that you could go and crash your machines and cause memory leaks and other things and then figure out if you could debug those problems. And I called it Not My Fault because when you screw up your server, it's not my fault. Now, but I'm going to intentionally crash this Azure server. Now, note that this app, let me see if, so it's at 5,000, 5,002. I'm going to crash. I just pressed the crash button. And tardigrade caught that. Server's rebooting. And we're back. That was so fast, we actually have time to do it one more time. So that brings me to the conclusion of the talk. I think just to recap what I showed you, I took you on a tour of our regions, our data centers. I took you a tour down memory lane and kind of gave you an idea of what we're doing with servers and some of the cool server hardware innovations we're doing. Then I switched to networking, talked a little bit about Bastion and Private Link and the way that we're making our infrastructure more secure for you, including at the networking level. Then storage, our scalable storage architectures, our disks that can fail over. And our fact that we're pushing more and more compute capability down to the storage layer where it can be more efficient. And then finally with compute, everything from pre-provisioned virtual machines to Azure container instances and at teleport for container deployments to Azure confidential computing, and then finally how we're focusing on making our servers and virtual machines even more resilient for you. I hope this was an informative view and it kind of excited you for where we are, not just where we are, but where we're going. I hope you have a great Ignite and see you in Azure. Thanks.